Okay, hello everybody. I'm Viviane Chouwaykanie. I'll be explaining session 2 of chapter 7, which is about the reaction between a weak acid and a strong base, or reaction between a weak base and a strong acid. So let's start by listing the objectives. Here actually there's just one objective, which is about to master the pH metric study of the reaction between a weak base and a strong acid. So it is the same objective of the session 1 of this chapter. The single difference that there we have used a weak acid with a strong base. Here it is the other way around. So there were some sub-objectives that will be the same: to write the equation of titration, to determine its Kr and to list its characteristics. Also we have to describe the shape of the titration curve in this case. We have to explain the value of pH half equivalence, and finally we have to explain the value of pH at equivalence. So let's start first of all. Titration of a weak base with a strong acid. Let's consider the following experiment. Here we have to add, to make the titration, we have to add a hydrochloric acid, which is a strong acid, to an ammonia solution, NH3, which is a weak base, and we will follow the variation of the pH according to a pH meter instrument of the mixture. As you can see, here is a pipette, and the NH3, which is the base of concentration that will be given later, with a volume actually VB equal 20 centimeter, is put in the Erlenmeyer flask or in the beaker. So this is just to be read, and this concentration, the concentration of the ammonia solution, would be indicated as CB, the concentration of the base. Now, here in the burette, we have to add the hydrochloric acid HCl, having an initial concentration of Ca equal 10 to the power minus 2, and you will know we will add HCl until reaching equivalence. As you can see here, this is equivalence, and we will be measuring the pH after each addition. Then this will allow us to trace the curve representing the variation of the pH as a function of the volume of hydrochloric acid from the burette. This is the curve, okay, which is made up, as you can see, of 4 parts. It is decreasing, and it shows two inflection points and 4 parts. It is exactly at the curve of the titration of a weak acid with a strong base, but there the curve were increasing. But in all cases we have 2 inflection points and we have 4 parts. The study of the curve, first of all we have the part Mn, where the pH decreases rapidly. Then we have the second part called NP. The curve shows a horizontal plateau. There is an inflection point. It's here. It's here. I called here I. Sometimes it is called I. There we didn't give it a name in the first session, but just you are trying to show you all the possibilities you can face in exercises. The pH decreases slightly. And the third part, which is PQ, the pH decreases suddenly. There is a drop of pH where the presence of the second inflection point corresponding to the equivalence point, and this is why it is called E. And the last part, which is QR, the pH varies again slightly, and the curve shows again a plateau. It would have an asymptote to a given line. Now, here at the beginning, in the beaker or in the Erlenmeyer flask, we had that species, which is an H3. And we have added H3O+. Don't forget that HCl is a strong acid, so it is represented by the pair H2O, H3O+. So the underlying species are the species that react together. Since it's an acid-based titration, a titration must be rapid and must be complete. This is why the NH3 would react with H3O+ coming from HCl in a complete way, giving H2O and NH4+. So this is the titration, and as I said last time, once we use the word titration, we have the right directly to write the equation with one arrow. It means complete. The reaction is practically complete, and as you can see, the Kr of it is equal to 10 to the power 9.2, so it's greater than 10 to the power 4, so definitely it is a complete reaction. How to determine the equivalence point? You know well. We have to use the method of the parallel to tangents, where we determine graphically the coordinates of the equivalence point, which is always equal. In this case, after all, when we have a base titrated with an acid, it would be VA equivalence and PHE, which is found graphically. Now, how to calculate the concentration of the titrated solution, which is in this case the base of unknown concentration. Typically, as we work, the equivalence point, you know, at equivalence, the reactant are their stoichiometric ratios. So N of NH3 presents initially in the beaker would be equal to the number of mole of H3 plus added from the burette. So all these are given except for CB in this case, so it will be calculated. Now, why the pH is acid at equivalence? And it's not neutral as 7, as we know here. Look at this. At equivalence, there is no more NH3 and there is no more H3O plus because they have added at equivalence according to their stoichiometric ratio. It means none of them is in excess. The single species present are NH4 plus and H2. Here, and definitely we have Cl minus, which is a spectator ion. Cl minus is an indifferent or spectator ion, as we said previously. We have H2O that is neutral, and we have NH4 plus that is indicated here, which is a weak acid that reacts in water according to a limited reaction represented as you can see here, it is reversible again. So look, the reaction of this ion with water, even in a limited way or in a limited way, it produces H3O plus ions, which renders the medium acidic. So the small resulting quantity, as I say, of H3 renders the medium acidic of the pH less than 7. Now, for the half equivalence point, what is the pH value of the half equivalence point? Here, it is a table that shows up the composition of the medium initially. Don't forget that here is a complete or a total, a complete reaction. It means we have to deal with it as if we dealt with the equation or the chemical reaction in grade 10, in grade 11, and even in grade 12. So we have to forget anything about equilibrium. Here it is a complete reaction. So at T0, we have N0, the number of mole of the NH3 which is present in the beaker, and no H3O plus were added from the burette. So the product would have 0 amount, and water, as you noticed, it's solvent, so it is always in excess. Now, what is the T equivalent? At T equivalent, the number of NH3 in the beaker that remains becomes N0 over 2. Here, it has reacted completely. This doesn't mean that it is 0. It means we have added from the burette H3O plus, but this amount has totally reacted with N0, and N0 over 2 NH3 remains. Definitely NH4 plus will be formed. Look how. As we said, at T equivalence, we have N of NH3. It is equal to N of NH4. It is equal to N0 over 2, as it's seen here. Okay, this is explained typically in session 1. So dividing by the same volume, both concentrations of the species present at half equivalence, which are the single species presents, is equal. Now what do we have to do? We have to apply Henderson-Hasselbalch to have pH equal pKa plus log to the base over the acid. This is the base and this is the acid. So log of 1, it will be equal. Again, pH is equal pKa plus 0. It means it's equal to pKa, as seen in the case of a titration of a strong or a weak acid with a strong base. So in both cases, at half equivalent, the pH equal to pKa. At the end, we have to compare the curves of titration between a strong base and a strong acid with a weak base and a strong acid. As you can notice here, this one consisted of 3 parts with 1 inflection point. Here, 4 parts with 2 inflection points. The equivalence point here, it's Va added, V of the acid, it means added at equivalence, and the pH is always 7 when it is a strong species. Here, no, the pH is less than 7. It is acidic, as we said, due to the conjugate acid coming from the weak acid. Half equivalence point is a concept that does not exist in case of strong, while here the equivalence point, the half equivalence, it corresponds when X of it means its abscissa correspond to V added at equivalence over 2, and the pH is equal to pKa of the pair, acid-base pair involved. Now, if we continue adding the volume of acid after reaching equivalence, it means when the volume of the acid added will be greater than that of the volume of the acid at equivalence. The curve, sorry, here it's in French, so excuse me. So here the curve will have an asymptote for the value of pH equals minus log Ca, and here it will add the same asymptote. So that's all according to our video. Thank you for watching, and you have to solve number 6 to page 186 in the textbook.